Yo, you guys could hear me, right? Type in chat if you could hear me. Just say anything. I don't know how to use this. Okay, cool. Just give me 1 second. I need to set up quickly. Okay. There's going to be some latency with when I talk and then when you guys hear it. Um, we're trying out this YouTube live thing for the first time, so I don't know how good it's gonna be. Um, but yeah. Alright, yeah, just wait a bit and then I'll start. Pretty sure this saves and records live as well. So here's hoping it works, but I can't guarantee it. Okay, I'm almost ready to start. I just need to open up some things. I need to open up the training package as well. I'm not gonna lie, I barely looked at it. I took a look before. It looked like a pain in the ass. I'm gonna open it. Oh, there's a part two? Yo, I didn't know you guys had a second training package. Wow, that's rape. Oh, what the fuck? This guy just copied last year's. What a what a lazy guy. Okay, that's fine. Um, yeah, I see what he did. He copied me. Armor's elbow. This is pretty straightforward. An effector. Yep. Let's go on Circle City. I'm gonna open up some things before we start. One more minute and I'll start it up. Just hold out. Yo, Abdul, what do you mean bonus? What are you talking about? I could plug in my webcam too. I gotta see if this works first. Let me see. My room's kind of a mess though, so I don't know if that's the best course of action. Give me Okay. Um, Let me know if you guys hear me. Give me a yes in chat. All right. Okay, so I'm gonna start this training with some intro. Um, I believe it's already in this training package, but I'll go over it again. So, Huang mentioned a few things during the kickoff meeting, saying how this year we're gonna build a 5-DOF arm. A lot of you guys won't know what the term DOF means. It means degree of freedom. That's what it stands for. And it refers to, so I have a definition here. You could read that. I wrote out my own definition. A degree of freedom relates to the motion a robot is able to move freely in. There are currently 6 degrees of freedom that like all of us could actually move in the real world, and that includes the X, Y, Z axis, and also the rotational axis about all of those, which is roll, yaw, and pitch. Um, so this image here is a perfect representation of all of the DOFs that you could that pretty much all the DOFs that is possible to move in. So all 6. If you see 6 different arrows here, so up, down, back, forward, left, right, roll, yaw, pitch. So when he means 5 DOF, that means that we're only restricted to 5 degrees of these arrows here, and that means we're losing one of these arrows. It depends on the design of the robot, but I think in our case we're gonna be losing like pitch or roll, something like that. Um, Most arms though, you don't need all of the degrees of freedom, and I'll show you how having 6 could benefit you. Um, so before I go into more depth about DOFs, what is a robot arm and what does it do? So a robot arm is just like your regular arm on your body. It's used to grab things, move stuff, type, whole bunch of functions that require fairly precise actions, precise movement, precise task, right? So in this case, a robot arm is pretty much the same as a human arm, but it's made out of mechanical and electrical components and it's controlled with software. So just search one up really quickly. Pretty straightforward. If you look at this one here, the way this works and how all of them work is it's a mechanical structure that connects motors together to move each joint. So in this white robot here, there's one joint at this portion, which we call a wrist. There's this one here, which we'll call an elbow, and then this main one here, which is the shoulder. So just like your regular arm, you have 3 main joints that connect your entire arm together. The shoulder, which is at the base of your body, and then from your shoulder, next is the elbow, and then from the elbow to the hand is the wrist. And that allows you to move your hand in a full 6 degree of freedom. So before we continue, as you see in this picture here, shoulder, elbow, wrist, same as a hand, an arm, shoulder, elbow, wrist, and the hand is just that end effector. With robot arms, the hands are more simpler than a regular hand. If you were to make a robotic hand, that would be called a bionic hand. It uses a combination of biomedical engineering, biology, biomedical science, and just like biomedical engineering is basically just biology with a mix of mechanical and electrical. Um, they're pretty simple. It may not look too simple, but each finger here, the way it works is it's controlled by a string, which is similar to like the I forgot what they're called. I think they're like the tendons in your fingers. So as you pull the string, it causes each finger to fold. And then with the hand, there's a few more fine tuning that's in it compared to like just five strings pulling on each finger to close them. The thumb has like a swaying motion, which is here, and then these fingers also like fold over a little bit more. Um, Obviously, we're not gonna be making a bionic hand. That's not what our group is. Um, it'd be a cool design team idea though if any first years are here and they want to start up a bionic or like a prosthetic club. Please let me know. I'll be interested in doing that next year. Um, but yeah, that's basically what the end effector is. It's just something at the end of the robot arm, which is why it's called the end effector, and it has different tasks. In our case, we just want a simple claw. Most end effectors that you could see on a full like industrial robot arm, it has different things on the end. So this one has like a tiny kind of like pincer, I'd call it. Um, but some have like suction cups at the end. So if we search up a Kuka arm, which is a Kuka is a big, I think it's a German brand. So in the end of their arms, they have like a base plate that they could attach end effectors onto. So this end effector here has a suction cup mechanism so that it could easily grab and pick up like flat objects like a box. Um, our end effector specifically that Huang wants you to make is a claw using this motor here. His choice for this motor is kind of brutal because I told him not to use this motor since the shaft is offset from the mounting screws. And for that, I would advise searching this motor up. This he did not give you it. Well, this motor is off of Servo City, so I believe it's a 9 RPM motor. I'll send it in our chat once I find it. But once you do find it, or once I find it for you guys on Servo City, you can just they have like a drawing that you could go off of. Yeah, so it's this. It's similar to this motor, but I'm just showing you as a reference here. On the web page, they have a drawing of the motor so that you see where this stuff is positioned, like where this center shaft would be positioned with respect to the mounting holes. So there's a little cheat that I'll give you there for now. Um, but yeah, so those are the components of an arm. Each of these motors for each joint is called an actuator. An actuator refers to something that allows rotational motion. Um, there's something called a linear actuator, which allows a mechanism to move in a linear motion. In this case, the robot actuators are rotational motion. So Huang provides these actuators in with these with like the wrist joint motor. Um, and I think yeah, you guys only have to make a wrist, if I recall. You don't have to make a shoulder joint, but you have to make the forearm. So what you're required to do is you're only making half of the robot arm. So you're making the end effector, which is the claw, and you're making the forearm, which is the structural component in between the elbow and the wrist. So you're not actually working on an elbow. You're not mounting anything to the end of this forearm. That's, I believe, something optional that he gave you for like brownie points. Uh, Yeah, so for brownie points, he would want you to create the rest of this. You're only required to make half of this. I think he drew it there. Um, I guess he didn't. Well, it's the other half that's not drawn here. Um, so I'll kind of go over how you could go about that. Before I do, um, so I covered that. So before I move on to how DOFs work on a robot arm, I just want to show you a few different types of robot arms. I know Huang provided some videos, which is this one here. This one's pretty straightforward. The two main ones that we use on our team is a Scara arm, which is kind of like what our current arm has, because there's a linear component that moves our arm up and down. And then there's a jointed spherical arm, also known as an articulated arm, which is what most robot arms are. So like this KUKA arm is an articulated arm. And it just means that it could be between 3 to 6 DOF. Um, what that means is if you look at the joints here, there's one motor here, one motor here, and one motor here. So the way it would move is kind of like a snake. I could cat that quickly in 1 second, but the more dots you add, it provides twisting motion. So this picture here highlights pretty much how the DOFs would work. Each actuator has two motions where it has a roll and a pitch. This one has a pitch um, and a roll somewhere here. This one has a pitch and roll. It's kind of hard to visualize in picture. I'll show you a better video later. Um, but that's kind of what it is. Something here you guys don't need to know about now. There's something called inverse kinematics. It's a mathematical process that a software will be using to control and move our robot. Um, but that's like something that you would have to know um, as a robot designer if you were to actually want to control it. Um, so finish covering all that stuff. Guess we will begin on actually how you will be getting started with your design. So, the thought process that I would do with going over this design is okay, first thing that Huang wants me to do here is make an end effector. So, obviously, you're gonna have to do research. I remember coming into R3, which is what we called it before. It was Ryerson Rams Robotics before our name change, and I didn't want to do any research. All I wanted to do was just straight design, straight like just go into drawing, go into the CAD and make it. But that's not the real world. If you see like there's like Chinese YouTubers, let me think of a good one. Go kart DIY. There's like Chinese YouTubers or like Indian YouTubers that will make a full-on like go-kart with no instructions or no manual or no drawings. They'll just start cutting, welding, manufacturing. That's not how the real world works because that you're asking for failure. So like the stuff that these guys do, it's cool to watch because you could gain like ideas off of it. This is like kind of how I started just watching a fuck ton of YouTube. I made a playlist a while ago called it's not on this account, but I made a playlist a while ago that I shared to Huang that just has a bunch of videos of cool things related to robotics or electronics or mechatronics or mechanical. Um, that could be helpful. So you could start there, just like robot search up on YouTube or Google robot claw, robot end effector. This searching it up on Google is a bit more difficult because it shows different types of end effectors, like this one here, which is a drill. Um, so you guys would just make it more specific, search up robot claw and figure out how they work. I do have so back when I was in first year, I was into robot claws and how different robot claw mechanisms work. So I have a sketchbook of various claw mechanisms, and it's just me trying to figure out how they work just from a picture and like a small video on how it's moving, and based off that small video I was able to sketch it out and figure out which points are moving, which points on the claw are fixed, and which points are attached to the motor. So like the simplest claw that you could make is something I I should have a drawing here. Something kind of like this where the two fingers of the claw have a gear on it, and you either drive one of these gears with a motor or you have a separate gear attached to this claw gear and that has a motor. So what do I mean by that? If you look at this claw here, essentially there's no motor on it. Let me find one with a motor. Actually, I have a good source that I could use, my website, if anyone is interested. Um, yeah, so this was my first year project that I made. So this is kind of like what you guys have to make. So right now I'm rotating the wrist, which rotates the claw. So this joint here is my wrist, and then that's my claw there. I have a servo connected to this gear, and that gear is connected to another gear, and these gears are linkages to a two fingers, and as you rotate one motor, the gear causes the second gear to move, and that rotation allows you to move the fingers of this robot claw. This was very simple because I use servos, but kind of show you how it moves there. Very, very simple. Once you start joining the team, you'll realize, oh, this looks cool at first. Once you understand it, you're probably gonna be like, oh, this is fucking shit. Like for a first year, what the fuck are you doing? This is an easy project. But not knowing anything at first, it is challenging. Once you begin to learn it, it's a lot easier. So this is what I was saying here. There's a servo connected to this link here, and that link has a gear which allows you to move the other half of the claw. This claw specifically is called a 4-bar linkage claw because there's 4 bars. So I'll pause it here. There's 1 bar here, there's 1 bar here, 1 bar here, and then this base joint is a bar, but it's a fixed bar, so that this second bar here, I'll call this bar number 2, can move freely in air, and then bar 1 is fixed. So you could do a 4-bar linkage claw. It's pretty simple. This one here is also a 4-bar linkage, but it uses a whole different mechanism. So instead of gears, it uses a screw here, and as the motor turns the screw, the nut in the center of here will move up and down, and that's something we called like it's pretty much a linear actuator. This mechanism here, where it causes an item to move in a linear motion. So that's one other idea. But yeah, I would start off with just searching up claw designs, YouTube shorts, YouTube videos, TikToks, Google images are perfect references on how you could do that. Just make sure that whatever you do, it somehow integrates this motor. Because if it doesn't, then you didn't you didn't make what Huang wanted you to make. So I'll show you one more design here. Um, You don't have to go as high tech as this guy. He made his claw have these like cutouts so that it's compliant, which means that it's like bendable. It could grasp against an object. You don't have to do that. If you want to make your claw have a compliant finger, go for it. I feel like for Huang, if he sees that, he's gonna be like, oh shit, this guy knows some mechanical knowledge. He's probably smart as shit. So it is brownie points if you do that. Some other claw designs, like our current ones, we put like a rubber grip. So if you look at this yellow piece is like a rubber grip on the end of the claw so that it could like grab it better. It provides a constant force. Um, if that's too difficult for you, you don't even have to add that rubber grip. You could just keep it without the rubber grip. So if you look at this one here, it's literally just 2 fingers with a gear at the end. This would be, I'd say, the simplest design you could make. If you're a first year, you're a little bit intimidated on how well you're gonna do. I'd say stick to uh stick to something like this because it's a little easier to do. It's a good start. But obviously it won't bring you to team A. It would you'd probably be team B. Okay, so next is the one axis our wrist joint. So when he says one axis, that means one DOF. So it only moves the claw in 1 degree of freedom. Um, Axis and DOFs can be interchangeable, but usually with axis, there's only 3 axes of motion, the Z, Y, X axis, and then you could rotate about those axes. But yeah, one axis is that's what he means by one axis. So if you search up robot wrist, hopefully we could find some sources. The issue with some of these sources, it might show you an actual bionic wrist, which is something that you probably don't want. Um, so let's see if we search up one axis robot wrist, that might be more specific. It's a very hard thing with this because you won't find like the specific video you want. You kind of have to watch videos on robots. I believe Huang attached this video to the training package, but this robot here is a three-axis or a three-off robot because it could rotate about here, and the base is able to rotate. So that's three different motions that it's able to do. And the wrist would pretty much be this motor here, and then this piece would essentially be your claw. So you have to figure out, okay, I have a motor here. I want to connect that motor to a claw, and then also this motor needs to be mounted to this forearm, which is this bar. So what you want to make is just this upper half. So this here is the wrist. Somehow a motor is mounted to that, and then and additionally the motor shaft is mounted to this piece here, which will be your claw. So that's what you're gonna be designing. The claw has its own motor, obviously, but once you figure out how to make the claw, then you could figure out how to mount that claw to a wrist, and then how to mount the wrist onto a forearm. So that means you need to figure out how to mount motors, and you don't learn this in school, but if you search up motor mounting, there's different ways you can mount a motor. If you look at this here, there's a bracket where this plate here screws onto this motor, and then it frees up the shaft so that anything that's connected to the shaft can freely rotate. So same thing with this motor. It has a bracket where there's a plate, and that plate allows you to screw in screws onto the mounting holes of the motor. So if you look at this motor, it's kind of hard to see, but there's actually four or five mounting holes. So if I zoom in, let's zoom in here. This is a mounting hole, this is a mounting hole, this is a mounting hole, and that's a mounting hole. So you have four mounting holes, and you would have to make some sort form of plate. It doesn't have to be a plate, but some sort of object that has holes so that you could screw, um, you could put screws into these holes to mount it onto an item. And then also it would need a hole here so that the shaft could feed through it. So that's how you'd mount a motor onto your forearm, whatever your forearm is. But one thing that you also don't learn in school is how do you mount an object onto a shaft. So motor shaft mounting. Let's search that up. So how do you mount stuff onto a motor shaft? So this motor here is called a stepper motor, and this long rod protruding out of it is called a shaft. This shaft will spin, and this motor here will like stay stationary. So as it's powered, only the shaft part is spinning, and that's kind of what you want. So to actually mount stuff onto this motor shaft, you could um, make a specific mount for it. So these here's are mounts, and the way they work is it goes onto the shaft of the motor, and then on the side of it, there's a hole which is a threaded hole used for a screw. And this screw, we call it a set screw. And what that does is it applies like a force onto the shaft, and it prevents it from sliding off. So that's one way you could do it. Another way is a clamping mechanism. So this mounting system would be called a set screw mount. Another mount would be a clamping mount. So let's search that up. Clamp. Um, that's not what I want. Might be difficult to see it. Okay, well actually this is good. So this would be similar to the mount that goes on the end of a shaft. And so you would put the shaft through this hole, and then there's a cut on the end of this so that there's there's like a bit of space, and there's a screw that goes straight through from this side to a thread on the other side. So if I take a screenshot of this, it's going to be a thread on this other side, and then the screw goes in from this direction. As you screw in as you tighten the screw, what happens is this cut here will begin to close in on itself, and this circular hole, what happens is it was once a circle. That's a terrible circle, I'm sorry. Um, it's once a circle. Once you screw it in, it kind of becomes like an oval, and that oval or that force from the clamp will cause it to stay on the shaft. So that's how you would mount something onto the shaft of the motor. You'd have to figure out your own um, your own mounting mechanism to get that shaft mount onto the claw itself. And then you'd also have to figure out a way to mount the motor mount onto the wrist that you're making. So I'm not gonna cheat here. I'm not gonna help you guys cheat, but I will give you some rough ideas on what I would do and what you could do. So I'm gonna proceed with caution right now because if I go too far, Huang is going to kill me. Um, so let's say, so I'm gonna download a random motor off of Servo City. I'm not gonna use the one that he gave you because then you guys have access to my video and you'll just copy it. So I'm gonna take a random one off of this website here. Um, so I'll take this. This website's good because you could usually download the parts on SolidWorks. I don't think you could download these ones. Huh. Alright. Give me 1 second. I'm gonna choose this one for now. What the hell? Where are these motors? Okay. Sorry. Just give me 1 second and I will get to it. So let me see what motor he gave. So he gave you that motor, so I'm gonna choose this motor. This is a different motor. This website already sells you mounts. You could use off-the-shelf mounts if you wanted, and then you would just mount your forearm onto these mounts. Um, I'll show you just like a quick idea on what I would do. I just don't know why I can't find these mounts or these motors. Oh, great, they're discontinued. Okay. So let's use this one. Ain't no way they don't sell. Why aren't any of the cats here? Yeah, so Huang said something in the chat. Sorry, let me just read the chat quickly. Would I be able to finish it if I gave myself 3 days? Yeah, it depends on like if you're spending the whole 3 days, that's crazy. You like I'd say 1 full day you'll be able to finish for sure. Um, you are allowed to use the design library toolbox. Yes, I wouldn't recommend making your own gears. It's a headache. Um, take it from me because I did that. It's been a while since I used it. It break a lot when used. Yeah, the toolbox is a little broken. You have to go on Google to figure out how to fix that. Okay, well this website doesn't have any of the things that I need, so I'm gonna go on a different website. If you see, I use a lot of different sites. Most of these are because of R3 or sorry, TMR. Damn, bro, these websites don't give the CADs for this stuff anymore. Interesting. Okay, Rev does. I'll use Rev. God damn. Why is it so much work just to get a fucking motor? Alright, I'm gonna take this one for now. Where is the CAD? Okay, well, I'm just gonna go on my files and find it. I don't know why I can't find anything right now. Uh, okay, let's use this. Sure, yes. Okay, we'll use this motor. So this motor here has a shaft. On that shaft, obviously the motor itself has these, how many is that? 7 mounting screws. So say we gotta make a wrist for, I'm gonna make a fake claw. So let's make a fake claw. So imagine somehow you finish the first step in like 30 minutes. Good for you. And you designed your first ever robot claw that mounts some form of motor. Um, Abdurrahman here said he didn't bother with fasteners. I don't know what Huang's rules is about fasteners. I know last year I said no to fasteners because it's hard to learn fasteners at first. It took me a while to kind of figure out how to use how to spec fasteners and all that type of stuff. Um, so you don't have to worry about that. Okay, so let's say this is my claw, and then I'm gonna put a hole here, some form of hole. Yes. Okay, and then this hole here is gonna have a set screw in the middle. So I'm just using, okay, I'm gonna do this slowly again because I realize a lot of you guys might not know how CAD or use SolidWorks. For those that decide to download SolidWorks, I'll do this quickly. So there's different tools, line tool, circle tool, square tool, whatever. Since I'm making a dummy claw, I'm just going to use line tool. You select the line tool, and then once you place a line, it continues to create more lines that are attached to each other. And you could keep placing them. And once you want to stop, you could either enclose whatever you're making and it'll stop the line tool, or you could hit escape on your keyboard and it'll stop the line tool from continuing. So let's say this is my claw here. Um, Smart dimension lets you dimension your drawing. So this is random sizing. I'm just gonna make this 70, make that 70, make this 15. There's another feature that you could do when you click on one line, hold control on your keyboard, click on another line. It selects both of them at the same time, and then on your left-hand window, there's something called the property view or the properties window. And under there, there's something called add relations, and you could basically add a relationship between the two lines. So if you want them to be equal length, you could hit equal, and that will do that for you. So I'm going to make these equal because it's the same thing. Um, Okay, so right now it's blue. If the lines are blue and not black like this here, it means it's undefined. So that means you could still move it. You haven't fully constrained it with dimensions or relations. So I think my last dimension here is this one, and then this could still move. So I will center this by selecting the origin, this line, and choosing the midpoint relation. So now it's fully defined because it's black. I could hit boss extrude to make this 2D shape into a 3D shape. So I do that here, and then you could set this dimension. I'll make it 10, arbitrary value, but a lot of the dimensioning portion that you're going to be doing is all arbitrary. There's no set dimensioning like number for you to use. It's just, oh, I think this looks nice and I wanted an even number, so I'll put 8. So that's kind of what I did here. I like the numbers 5, 10s, and even numbers, so 2, 4s. I don't like 6, so I usually keep it to 2, 4, 5, 8, and 10s. But that's just my preference. Everyone has their own preference. So this is my dummy claw. Imagine somehow a motor mounts onto it. I'm not going to add the motor. And then I need to add some form of mounting system so that this motor shaft can mount onto this claw so that it works as a wrist. I'm going to make something simple here. So like that set screw mounting mechanism that I showed you earlier. I'm going to make a hole for that shaft to go in. So you take that shaft and you would measure it. Um, the way you would measure it is figure out what the part number is, go to Servo City, type in the part number, and then when you open up the motor, there's going to be a drawing um, on the web page. For my case, I don't know what this motor is, so I'm just going to choose evaluate and hit measure, and then click on this here to get the radius. So the radius is 4 millimeters. That means it's 8 millimeter in it's 8 millimeters in diameter, so I'll make that 8. It's a pretty big hole. Okay, let me make this a little thicker since the hole is so big. And then I'll center this. Okay, that's 8 millimeters. Now last thing is just to fix this so that it stays at this point. So I'm gonna take this here and take this center point and choose vertical, and basically fixes it so that this point is always vertical about this origin point. Um, and then I'm gonna cut extrude to make a hole into the part. So 15, arbitrary value. You could make it the length of the shaft. But if you make it the length of the shaft, remember you have to take into account the mounting plate or the mounting point on this motor itself. So I'll only do like 2/3 of the length. So let's measure this. That's not the right thing. Measure, so hit that, hit that. Okay, measure tool doesn't want to work. So it's 31.5 millimeters SolidWorks, and if you're using Onshape, it's pretty nice because you could put equations into them. So I will put 31.5 times 2 and then divide it by 3, and it will do the math for me. So 21 millimeters. So we made a 21 millimeter hole for that shaft. Now I have a few options. I can make a set screw so that it applies force onto the shaft and it holds it in place. Or I could do the clamping mechanism. With this design here, it's a little bit harder to make a clamping mechanism because I would have to have that clamping screw, and it'd just be more work. You could do it, you just have to figure out how to make it. There's another thing that a lot of modern machinery uses nowadays. It's called a keyway. So shaft keyway, what that does is it couples the shaft onto some whatever you're putting the shaft onto. It couples it so that it could rotate together. So the reason why we're mounting stuff onto a shaft is so that it could rotate with the shaft. Um, this keyway, the way it works is you would have to make a keyway into your part, and then your shaft would need a key seat, which is this component, and then you would also need a key, which is like a piece of metal that seats into the key seat, and it also slides into the keyway. So if you look at the shaft that we're using, it has a key seat. So if I wanted to, I would just cut a keyway into this hole here and then put a key into it. The issue with this though is what it does is it couples it when it rotates, but that means you could still slide it in and out, and that's not the only thing you want to do. You obviously want it so that it can't slide in and out, and it could also rotate the part. So in this case, we'll just stick to a set screw because it's simple. Um, I don't think it's too big of a deal if you have a set screw in yours. I know last year one thing that I was testing on is to see if people would incorporate a set screw or some type of clamping mechanism, which they didn't. So this year I'm just gonna teach it because um, it's kind of hard to know if you're not a third year because you learn it in third year. So I'm gonna change this to up to next, which cuts it up until the next like contour, the next face. So it only cuts up to there, it doesn't cut straight through the part. And this is my little keyhole. You could be a little extra and choose the thread feature to cut a thread into this hole. I'm gonna do that for like right now, but you guys don't have to do that at all. This is just me being extra. I made this hole 3 millimeters for a M3 thread. Nice. M3 is not even here. M2. Oh no, it is. M3. Okay. Um, that's good. It only needs to go up until I'm gonna make a guess and call it 8. Yeah. No, 8 is too much. Let's do up to selection. So up to this point, or up to this point. Do that? No, that doesn't work. Okay, that's fine. I'll just do blind. So we'll do it for 4 millimeters. Like I said, this is completely optional. Use extrude, yes. So just makes a thread here. This is extra as fuck. You don't have to do it, but I'm just trying to show you like this. The set screw hole has a thread so that you can put a screw straight through it. So now let me show you how this wrist is gonna work. So we'll make an assembly. Let's save this. Where should I save this? Dummy claw. It doesn't look like a claw, but it will work. So make assembly. And then add that motor in. And then pretty much just mate the shaft onto this hole, or like the claw mounting point. This is just arbitrary, obviously. Um, Shit, I can't see the inside of that. Hit that, hit this. Good thing with SolidWorks is it automatically mates. For those using Onshape, you have to choose the specific mate. So the tutorial will kind of go over that. Do you need to design parts with tolerance? No. So you don't need to incorporate tolerance in your part. That's something, so usually when you're designing parts in SolidWorks, you could add a tolerance feature to your dimensions, but usually the tolerance is easier to do in your drawing that you're going to send out to manufacturer. So none of these are actually getting made, so you don't need to tolerance them. But if you were to make it, let's say, if you were to 3D print it, you would have to like undersize certain dimensions or oversize certain dimensions so that it fits properly. If it's to be made out of like metal, you would make like a part drawing, and then from that drawing you would add tolerancing to your dimensions. But for something like this, you just dimension it so that it could like mate in assembly, and that's perfectly fine. But um, I don't think we're really looking for tolerance for something like this, so don't worry about it. Okay, so this motor here, this wrist motor connects the um, fake claw here. I just made that float because with assemblies, the first object you place in is always fixed. So float just lets you move it. I'm gonna fix this so it doesn't move. So if you see, it's mounted, so this motor, as you power it, what it should do is it would rotate this claw here. So that's essentially what you want. And then the next thing you want is you want the forearm, which is literally just a structural piece that goes from this motor here, from the wrist motor, uh, from this wrist motor to whatever the shoulder motor is going to be. Um, Huang, did you want the wrist to move the claw this way, or did you want the claw to tilt? Because if you want it to tilt, then this design that I just showed is flawed. So they could choose. So what I just said there, usually a wrist, the way your wrist works, if you have your, if you look at your hand right now, you try moving your hand, you could rotate it, and then you could also move it, like you could rotate it down and up. Um, so that's 2 degrees of motions because you could rotate your hand and then you could pivot it up and down. So this here is just provides hand rotation. It doesn't provide that like pivot up and down movement where like it goes down like that and then it could pivot up like this. So if you were to want to do something like that, then this design here won't work. You'd have to do something else with how you mount it. So you need to mount the motor like this, let's say, and then mounts. So I could do that quickly just so that you kind of understand the other option. So let's say the wrist starts here. It's gonna start getting a little ugly, but it's a good way to show. Oh, that's not. What? It's not intersect the model. What are you talking about? The intended cut does not intersect the model. Okay, let me see what's wrong with this. I don't know why my thing is tripping out. think I accidentally did a extrude cut. So say you have this piece here. Let's do another set screw. I'm gonna do this quickly because I just want to show you the idea. So with this type of wrist, obviously you could make this centered. I didn't make it center, but basically the claw would like rotate. Um, not, it wouldn't twist. It kind of like, I don't know what this would be called. I think this is like a tilt. So let's call this a tilt. So yeah, you'd make it tilt kind of. Let's add this mate as well. So you have the choice of either mounting the wrist the twist way or the tilt way. And then from there, yeah, you'd make some type of limb that connects this. It'd be a structural piece that connects this motor to essentially a second motor, um, as seen in this drawing here, where this is the wrist motor and then this is the second elbow motor. So you'd have to make this gray piece here. So that would be your forearm. And that's essentially what Huang wants you to do for your submission. Um, it incorporates mechanical design in the claw, and then it incorporates structural design in the way you make your forearm. So when you're making something structural, um, so let's search up structural support. There's different ways you can make it. You can make something that's just like thick and strong, but that's very simple. You can make it light and sturdy. So like I-beams, for example, is something that was invented to reduce kind of weight, but also make something sturdy. So it's very hard to flex an I-beam. You'd want the same with a robot arm. You don't want it to be able to bend. So the way that you make your forearm has to be structurally sound. You just gotta figure out how you would do that. Um, yo, is this Ryan Leaf, the fucking mech? I know the software lead. What the fuck? What are you doing here? You could do a tube. Tubes are very good because they take loads very well, but they're bad, I think, torsional. So there's different factors with every type of structural component. This here is pretty much just a plate. Plates work fine too. The only thing is they could bend in the opposite direction. Um, you could do like multiple plates. Let me find an idea. So this is a box tube, so it's kind of like a square tube. That also works. More round tubes. Obviously, if you're doing round tubes, you have more problems with mounting each component, but it's possible. You just have to make a custom piece. Square tubes is a little easier, and then plates are easy too, but that's way too simple. You just gotta figure out how to make it a little bit more rigid. Um, I don't, I don't see a plate design. This is kind of a plate design, but it's not the same type of arm. It's a different arm. I'm gonna show you one last picture and then we'll end it here. So yeah, this is kind of like a plate where it's like one plate on that side, one plate on that side. So that's kind of what I mean by plates. You kind of need like two identical plates next to each other, and then somehow you like support it through a beam so that they're kind of strong enough. Um, but yeah, that's how you would go about making the forearm. It's the structural component of your design. That's those are the two main things we're kind of looking for. Last year we were looking for something different. This year Huang wants some mechanical and some structural, because the structural shows like more of your creative design on like making things look good but also strong, and then the mechanical design is how well you could integrate mechanisms together to make something that moves. Um, so I will be accepting questions now. I finished what I'm going to be teaching today. On Sunday, I will be going over just CAD, how to use Onshape, how to use SolidWorks, and answering more questions. But today was more so intro and brief on how to actually complete this module. So if you guys have questions, start asking. I will accept them. Nah, this definitely has to be fucking Ryan from software. There's no Ryan Lee in mechanical. This guy's a capper. Alright, if you guys don't have any questions, I will be leaving. Um, I'm gonna share this document here. This is something that I made um, a while ago for some team members, but I'll share this in chat. I haven't joined the server yet. What the hell? If you didn't join the server, how'd you get an invite to this fucking YouTube live stream, you fucking liar? What's wrong with this guy? Okay, no one's gonna ask a question. I will be signing off. I hope that answered, or I hope that cleared it up for you guys, and I hope it makes it easier for you to complete this package. Um, Make sure that you do ask questions in the Discord chat when you need them. Last minute questions are worse than stupid questions that you ask now. Remember, there's no well, there is such thing as a stupid question, but usually those stupid questions would be asked by another person. So don't be scared to ask a stupid question because someone else will definitely be asking it as well. I hope you guys have a good night. I am going to bed.